Imagine a plane that had the capability to fly 10 times higher than any commercial jet and at speeds of Mach 25, fast enough and high enough to go into orbit around the Earth, drop off a payload, then return and land just like a normal plane. Unlike rockets nowadays, there would be no need to detach stages and it would be completely reusable. Is this the future of space travel, and is this technology enough to completely replace rockets? Hello everybody, welcome to Future Leaps, a channel where we look at everything in science, technology, and engineering to learn about what they are and discuss what potential they have for the future. Today we will be covering the Skylon Spaceplane, a vehicle design that could play a huge role in sending people to outer space. Spaceplanes are a popular concept, and many people believe that they can compete with modern-day rockets due to their low costs. Skylon is a spaceplane concept based around Saber, an engine design which is currently being developed by Reaction Engines Limited in the UK. I selected this specific spaceplane concept because its engine has a very unique design that transforms throughout the flight. Based on altitude and speed, the engine's intake and nozzle adjust their shape so that their thrust is always produced efficiently. Let's look more closely at the mechanics of Saber and how it achieves this efficiency. When the plane is flying below Mach 5.14 and below 28.5 kilometers, it functions very similarly to a turbojet engine. At this stage of flight, the engine is in its air-breathing mode, so the front of the engine, called the inlet, is open. The air intake goes through the pre-cooler that lowers the air to negative 150 degrees Celsius, then through a compressor, which increases the pressure of the air to 140 atmospheres. Now the almost liquid air is optimal for combustion and moves forward to the combustion chamber, where it is then ignited with hydrogen gas. The exhaust leaves through the nozzle and produces forward thrust. When compared to a normal jet engine, the principles are the same, but there are a couple differences. For starters, a turbojet engine typically has no pre-cooler, and instead, the intake goes straight to the compressor. The reason for this is that at low subsonic speeds, the air has a low kinetic energy and thus a low temperature. However, since the Saber is designed to handle supersonic speeds, anything above Mach 1, and hypersonic speeds, anything above Mach 5, the air has a lot more kinetic energy and thus is much hotter. In fact, the air intake can be as hot as 1,000 degrees Celsius. Another reason the cooling phase only appears in Sabres is because a typical engine will combust at higher temperatures since they are using fuels like kerosene. But on the other hand, Sabres use hydrogen and will need sub-zero temperatures. When comparing the engines again, you'll notice Sabre has no turbine after the combustion chamber. Typically, the turbine uses the exhaust air to generate torque, which is then used to spin the compressor. In Sabre, the compressor is powered by the helium loop. Now, the helium loop is a unique feature. Helium gas circulates around the engine, redirecting heat. The helium loop is what collects heat from the pre-cooler, and it redirects that heat to vaporize the liquid hydrogen fuel before it is directed to the combustion chamber. The heat is also used to power the air compressor, the hydrogen pump, and the liquid oxygen pump, which will be used later in the next phase of the engine. The last notable difference between typical turbojet engines and Sabre is the adjustable nozzle. For the most efficient thrust, the engine's exhaust must have the same pressure as the environment. If the pressures are different, the exhaust will create this bell shape, and the exhaust will not be moving parallel to the engine. This means that momentum is dispersed and the engine is thus less efficient. Since the ambient pressure changes with altitude, engine efficiency is never constant. However, Sabre solves this problem because the adjustable nozzles can change the exhaust pressure to match the ambient pressure. And this is an important innovation, and it is what allows the engine to work at sea level and in space. For comparison, the pressure at sea level is 101 kilopascals, and at 28.5 kilometers, it is only 452 pascals. Rockets will typically have 3 engines, each with different exhaust pressures to fix this problem, but now Skylon can go up to space with just 1. Once the plane has reached the previously mentioned Mach 5.14 and 28.5 kilometer altitude, the air is so thin that the oxygen intake is not enough for the engine to perform efficiently. As a result, the engine transforms into rocket mode, and the inlet's new shape prevents air from entering the compressor. Instead, the engine uses onboard liquid oxygen to power the engine, which, after the total burn, is enough to speed up Skylon to the desired Mach 25. Overall, the Saber is a beast of an engine, able to accommodate flight throughout the entire mission, handling a wide range of air conditions. Not only does it remove the need for multiple engines, but it also performs better than most other engines. The thrust-to-weight ratio of Saber is 14, which is a massive improvement from turbojet engines, which are about 5. Specific impulse is the efficiency of a propulsion system for spacecraft, represented in seconds, where a higher time means the engine produces more thrust for the same mass of fuel. The Saber engine-specific impulse is a maximum 3,000 seconds, which is very high compared to the typical 200 to 400 seconds seen in rockets. If these numbers prove true after more testing, this engine will be deemed one of the best options for space travel. Now that we've unpacked how the propulsion system works, let's look at the design of the spaceplane. Immediately, you'll notice that the majority of the fuselage is fuel. Here we can see the liquid hydrogen fuel used for both modes of flying, along with some liquid oxygen used for the rocket mode. The benefit of using hydrogen fuel is that it is extremely light, which means Skylon requires less thrust to achieve orbit. This allows for the payload to be larger in relation to the rest of the vehicle. Weight is important to minimize with spacecraft, so Skylon is made out of titanium reinforced with silicon carbide fiber, a strong and light material. A ceramic composite skin on the bottom prevents heating up due to re-entry. The spaceplane can control attitude during air-breathing flight with its forewings, ailerons, and a rudder. After the rocket mode, when main engines cut off, small RCS engines in the front and rear take over to allow for orbital entry, exit, and attitude changes. Skylon has a cylindrical payload, 13 meters long with a diameter of 4.8 meters, long enough to fit a school bus and tall enough to fit a giraffe. The payload has a maximum weight of 17,000 kilograms to low Earth orbit, or 7,300 kilograms to geosynchronous orbit. Given this information, the payload is large enough to house up to 30 astronauts, which is a number very few spacecraft can boast. Now that we've covered Skylon's design, let's look at its cost and feasibility. I'll be comparing it a lot to SpaceX's Falcon 9 because they're both fully reusable and have similar payload sizes. SpaceX is ahead of reaction engines in terms of development and practice, so it'll give us a more realistic view on Skylon's future potential. Now this is not to say one is better than the other, and as we will discuss, they both are unique and hopefully they both continue to be developed. In terms of cost, we know reusable rockets are drastically cheaper today. As seen in this chart, the Falcon 9 is nearly 15 times cheaper than the Space Shuttle when looking at its cost per kilogram. The newer Falcon Heavy is already half the cost of the Falcon 9, which can be attributed to its massive payload capacity. When looking at Skylon, the research and development costs are about $12 billion, and the current cost projection for one unit is $260 million. However, Skylon spaceplanes are theoretically able to complete 200 orbital flights, so this will bring down the cost drastically. With these numbers, it is estimated that sending a kilogram to low Earth orbit would cost $1,500, and they hope to bring this number down to $900. Keep in mind that this is very early on in the project to have an accurate cost estimate, and this number will likely change. When compared to the Falcon 9, the cost to low Earth orbit is $1,900 per kilogram. However, SpaceX is hoping to get that number down to $1,100. At this point, it is hard to say which is a better deal. SpaceX has already had many launches and is currently generating revenue, so their numbers are likely more accurate than reaction engines. However, if the Skylon estimates do not increase throughout its development, it might be able to cut costs slightly. Another cost is in infrastructure. Reaction engines will need to create its own special runway to accommodate Skylon, and will need a hangar to store and do repairs in. This might add costs in the future, costs that SpaceX has already paid. In my personal opinion, Skylon will end up being more expensive than reusable rockets, but I still see its place in the market since cost is not the only factor. Skylon may be the better choice for human flights. As mentioned before, theoretically it can carry 30 astronauts. If, in the future, there's a need to send a lot of people into space, maybe for tourism, Skylon can get it done in less flights. Also, it can be assumed that the flights will be much more comfortable. Astronauts on rockets experience really high G-forces, and it is not an easy task. However, a spaceplane would feel more like a plane flight. Although it reaches really fast speeds, the acceleration is much slower. In fact, it takes over 15 minutes to reach space and 45 minutes on re-entry. Although it won't be as comfortable as a typical red-eye, it definitely beats being strapped onto a rocket. Skylon might also benefit from having a shorter turnaround time, a safer abort system, and more flexibility with launch times, since weather does not affect planes as much as it does rockets. As a result, I think Skylon will be able to provide flights more consistently. Overall, Skylon has a few key differences from Falcon 9 and other rockets. It is more human-friendly and can launch more consistently. However, the Falcon 9 is more fully developed and tested, so it has that inherent advantage. It's important to understand that this is not definite, and Skylon is still very early in development. I believe both spaceplanes and reusable rockets have their uses, and I hope both receive the funding and support they need to keep innovating. Their contributions to space travel are great, and will allow for many more space projects to be achieved in the future. I do plan on doing more videos on different forms of transportation and on some astronautical projects, so if that interests you, please stay tuned for more. Thank you so much for watching, and as a thank you to making it to the end, here's a fun fact.